Introduction to differential equations. Then we'll start ordinary differential equation. Okay then. So what are ordinary differential equations of first order? Yeah, very first we should learn that what is actually the definition of a differential equation. A differential equation is an equation which is having dependent variable y, independent variable x if we have a relation y as a function of x. Okay, so a differential equation has variables, either there are one independent variable or more than one independent variable, right? So of course there is one dependent variable having one or more than one independent variables. Of course, the differential coefficient of dependent variable with respect to independent is also present. Alright, so anywhere in any relation, if we are finding a differential coefficient present there, then we call that as a differential equation. Alright, so that's what is mentioned here, that if an equation which involves differential coefficients as well as dependent variables also, I would say. So that equation, that relation is known as differential equation. Alright, so as it is mentioned here in the first equation that dy by dx is equal to x squared minus 1. It's a simple linear differential equation of order 1. In this example, let us have this example as second example of differential equation. D2y over dx2 plus 2 dy by dx whole square plus y is equal to 0. It's also an example of an ordinary linear differential equations with order 2. Okay. It's also an example of a differential equation which you must have seen in your previous classes, right? Alright, this is also a form of differential equation. Let's call this as fourth example. Here, this is once again an ordinary differential equation which is having product of differential coefficients as well, and its order is 3. Right? Another example we have taken here also. This is one of the jumbled form of the differential equation actually, where we have not simplified, this simplified differential equation. So why it is not in simplified form? Because it is power of power. So we should simplify it and then it would be in the standard form. This is also one of the forms of differential equations. It is very much familiar for you. We have done this differential equation, which is nothing but ordinary partial differential equation, which is nothing but the Euler's formula as well. Right, it is what? It is second order partial differential equation. Okay. Yeah, so these were some examples of various types of ordinary differential equations of various orders, right? So our module is actually ordinary differential equation of first order. We have to start with this, okay? Right. Yeah, differential equations which involve only one independent variable and the differential coefficients, let me pen, one independent variable and the differential coefficients with respect to it, means if y is dependent variable, x is independent variable, so we must have the differential coefficients, whether these are total differential coefficients or partial differential coefficients, del y over del x. Alright. So in this way we can form a differential equation. Yeah. So in previous examples, 1 to 6 means so many examples we have noticed here. From this to this, we can notice that all are ordinary differential equations. Alright, and differential equations which involve two or more independent variables and partial derivatives with respect to those independent variables are there, then that is called as partial differential equations. Alright, which I have told you already. Yeah, here in 7 and 8 examples, just go back to the previous slide. This example number 7 and this example number 8, both are what? Having differential coefficients but in terms of partial derivatives. Alright, so partial differential coefficients we have here, so that's why these are partial differential equations, right? The order of a differential equation is what? The order of a differential equation is the order of highest order derivative present in the differential equation. Alright, so I'm going back to the previous slide here. So if I notice this example, here the differential coefficient is dy by dx. What is the order of this differential coefficient? It is 1. Means 1 times y is differentiated with respect to x. So that's why it is first order differential equation. Right. Here coming to next example, the highest order derivative or highest order differential coefficient present in this equation, differential equation, is what? 2. It is nothing but 2 times differentiated. So y is differentiated with respect to x 2 times, right? So the order of this differential equation is 2. Right? So I hope order of a differential equation would be clear. Right. Equation number 1, 3, 4 are of first order and 2 and 6 are of second order, while 5th is of third order. Just going back to the previous slide. Yeah, here you can notice that this is of second order differential equation. How can we find out its order? Let me solve it. Here it is 1 plus dy by dx whole square raised to the power 3 by 2. So to remove this 3 by 2, what should I do? I'll take the whole power is 2 by 3 of the whole equation. Understood? Yeah. So I'll take whole power as 2 by 3. So this becomes 1 plus dy by dx whole square is equal to k raised to the power 2 by 3 and d2y by dx2 is having the power 2 by 3. Alright. Now this is a differential equation which is in simplified form, right? So also the highest order differential coefficient present in this equation is d2y by dx2. So that's why its order means the order of this differential equation is 2. Alright. Yeah. Now coming to the degree of a differential coefficient. Degree of a differential equation is the degree of highest order derivative which occurs in the differential equation provided the equation has been made free from radicals and fractions as far as the derivatives are concerned. right? So now to explain this degree of a differential equation, I'll go back to the previous page here. I have just simplified this differential equation where I have removed this fractional power, right? So I have made this differential equation free from radicals, or we can say that surds. So there is no surd now present in a absent manner, right? So here the highest order derivative is what? d2y by dx2, right? So the order of this differential equation is 2. So the power of this highest order differential coefficient is known as the degree of differential equation. Understood? So its degree would be 2 by 3, right? All right, now let us check about this example number 2 that we have. Yeah, here in this example we have the highest order derivative present is of second order, that is, yeah, it is d2y by dx2. So the order of this differential equation is 2. What is the power of this differential coefficient? It's 1. So that means the degree of this differential equation is 1. Got it? Now coming to this one more example, number 5. Here we need to search what is the highest order derivative present. So it is d3y over dx3. So that means its order is 3 and the whole power, that is 1. So we call that degree of this differential equation is 1. Understood? So in this way we can find out order and degree of any differential equation. I hope I'm clear till now. All right. Yeah, now let's switch to solution of a differential equation. What is solution of a differential equation actually? So if we are given a differential equation like this, that we have fx dx is equal to some gy dy. Okay, so it is easier to find out the solution. How come? If we integrate both the sides, we are able to find out y as some function of x plus constant of integration, right? But if we have no such relation, then it is necessary to understand that how we are going to have the solution. Means if y is dependent variable, then we should have the solution of differential equation as y in terms of x, right? Yeah. Now coming to a solution of differential equation is a relation free from the derivatives. We know this point very clearly. Between the variables which satisfies the equation which is given to us, right? Okay, so if y is equal to fx be the solution, then replacing y and its derivatives with respect to x in the given differential equation, we may have the solution. Okay, so for example, here we have y is equal to c1 cos x plus c2 sin x. Then how can we say that it is solution of this differential equation? Okay, this differential equation is, yeah, it is mentioned here. So what we have to do here, we'll differentiate this given solution once dy by dx is equal to minus c1 sin x plus c2 cos x. Once again, we'll differentiate it with respect to x itself. So once again, differentiating, I'm getting this result. Alright, so after taking negative common, I'm having here c1 cos x plus c2 sin x. That is what? Y, which is given to us. So it's minus y. Right, that means we are reaching to the differential equation from the solution given. Right? So this is vice versa. We need to find the solution of this differential equation, which definitely is going to be this result, which we will learn in the further slides. Okay? Right? So in this way we can understand what is actually solution of a differential equation. I hope this would be clear to you. In successive slides, I will show you that how can we form the differential equation with the help of the solution given. Yeah, so here what we have done, here the solution was given and we have formed the differential equation as well. Alright, so in this way we can find the solution of differential equation. Now let's understand what is the journal solution or complete solution, right? So always remember the differential equation whose order we know. Its solution would always be having the number of arbitrary constants equal to the order of the differential equation, right? I will make this point more clear. As if I am having nth order differential equation, right? So its solution, its journal solution should have n arbitrary constants. Then that would be known as journal or complete solution. Alright? Yeah. So here it is mentioned that journal solution of a differential equation is that in which the number of independent arbitrary constants is equal to the order of the differential equation. That's what I have told you just now. So here, thus in this solution, y is equal to c1 cos x plus c2 sin x. Here we have two arbitrary constants as c1 and c2. So that's why this is journal solution of this differential equation, which is of second order, right? And what's degree of this differential equation? It's 1. Alright. Now, let's understand what is this term particular solution. Actually, the journal solution or complete solution involves the two part of the solution, which is if I am having the differential equation mentioned in journal form like this, if dy is equal to q. What is if d? D, we know that d is what? Differential operator. Alright, d by dx. So this is a polynomial in differential operator. Y is dependent variable and q is the function of x only. Alright, q is the function of x only. Okay, so here the solution of journal solution of any differential equation consists of two parts. One is complementary function, right, which is shown here with the help of some example, and another one is particular integral, right? So complementary function is the solution of left hand side part, and Particular integral is the solution of right hand side part. Understood? Okay. So now let me remove all the written material. Yeah. Particular solution of a differential equation is that which is obtained from its journal solution by giving a particular values to the arbitrary constants, we can say. For example, y is equal to c1 e raised to the power x plus c2 e raised to the power minus x is the journal solution of differential equation d2y over dx2 minus y is equal to 0. Whereas y is equal to e raised to the power x minus e raised to the power minus x or this are its particular solutions, right? Because the differences of arbitrary constants C1 and C2. Because these two are not having arbitrary constants. So that's why it's not a journal solution. These are particular solutions, right? Okay. The solution of a differential equation of nth order is its particular solution if it contains less than n arbitrary constants. Okay. A singular solution of a differential equation is that solution which satisfies the equation but cannot be derived from its journal solution. Alright, so this is the definition of a singular solution. Okay. Next, formation of a differential equation. Right, how we can form a differential equation where we are given two types of solutions, where it is when the solution is given in terms of arbitrary constants, like it is given here c1 c2 c3 and so on cn, right? So this is solution given to us. So by eliminating n arbitrary constants, we can form a differential equation of order n, right? Yeah, this is the procedure. We differentiate the given solution with respect to x and try to remove all the arbitrary constants. Hence, we continue differentiating till the desired arbitrary constants are not removed, and we continuously using the previous results which we are continuously obtaining, and hence we reach to the result that is having no arbitrary constants, and we must be having the differential coefficients of various orders, and that is nothing but our nth order differential equation. Alright, hence this also proves that a journal solution of nth order differential equation has n arbitrary constants. Alright, yeah. So I'll show you how by removing the arbitrary constants we can establish a differential equation. Okay, so for example, I am having the solution like this: y is equal to 1 or c1 plus c2x plus c3 x square plus c4 x cube. I can write here. Okay, right, so this is the solution given to us in the form of 4 arbitrary constants, right? Now we have to remove these arbitrary constants from the solution, so as a result of which we are going to have the differential equation. Understood? Okay. So let us start differentiating. So I am going to differentiate this y once with respect to x. So I am getting this as c1 0 means c2 plus 2 c3 x square x square is there, means x raised to the power 2 minus 1, that is 1, plus 3c4 x square. Got it? This was c2 into 1. Let me erase it. c2 into 1 plus. Next, this term is differentiated, 2c3x plus next term is differentiated, 3c4x square. Right? Now, one arbitrary constant is removed, rest 3 are left. Okay, once again I'll differentiate it. So I'm getting c2 as 0 plus 2c3 into 1 plus 3 2s are 6c4 into x. Right? Right. Now we are left with 2. Okay, so y triple dash means third time derivative. I'm having 0 plus 6c4 only. Okay, so now c4 is left. So once again I'll differentiate it. This is fourth derivative and I'm having 0. Right? So already I was aware about the order of differential equation, that of which order differential equation I'm going to have with this solution. How come? Because here I was having 4 arbitrary constants, C1, C2, C3, C4. So this gives me an idea that how many times I should differentiate this solution. Alright, so that's why I've differentiated it 4 times and that's giving me the result. Okay, so in this way we can form the differential equation by removing arbitrary constants from the solution. Alright. So another method is also there, following which we can form a differential equation once again, and that is known as the method of formation of differential equation by removing arbitrary functions. For example, I am having y is equal to phi 1 of x plus phi 2 x. Right. So here I am having two functions, phi 1 and phi 2. So these two functions we have to remove. So if anyhow we can remove this, and this will depend upon the function what is given in the question. If we are able to remove these functions, then the resultant would be our differential equation. So of course we need to differentiate it, right? So whatever the method we follow to form the differential equation, definitely we have to differentiate the solution, right? And that will give us the differential equation. So in this way we can form differential equations as well. Alright, so I hope till now all the points would be clear. So I'm closing this video here. In the next video we'll meet again.